Okay, let's start. We're very happy to have Cody from Cornell Tech. He's going to talk about SPARKS, Succinct, Parallelizable Argument of Knowledge.
Thanks, Gilad, and thanks for inviting me. So yeah, I'll be talking about SPARKS. This is joint with Naomi Ephraim, Ilan Komargatsky, and Rafael Pes. And I want to emphasize that feel free to interrupt at any point in time to ask questions. I'll try to leave pauses in certain places, but just interrupt me. It'll be hard to see, like, I don't know, your faces and stuff while I have my full screen presentation. And also, since some of you may have seen this talk at Eurocrypt in some abbreviated version, I think it's even more important just to interject and ask questions. So yeah, as Gilad said, what was that?
I said thanks, good.
Okay, cool. So as Gilad said, I'm talking about SPARKS, which are succinct, parallelizable arguments of knowledge. So to start off, I want to just recap a kind of more standard notion, which is succinct arguments for NP. So this is where you have some prover who's interacting with some verifier as to whether some statement X is in some NP language L. And because this is an NP language, to capture kind of efficiency, we also provide the prover with the witness for this relation. So what do we require from succinct arguments? First, we require completeness, which says if the statement is in the language, then the verifier will actually accept this interaction. The soundness property is that if the statement's not in the language, then no computationally bounded prover can convince the verifier with at least noticeable probability. And in fact, in this work, we'll consider a stronger notion, which is that of argument of knowledge, which says if the prover does convince a verifier, then it actually knows a witness, where I'm keeping this informal, but just know that this kind of stronger requirement is what we're considering in this work. And kind of the last and maybe most interesting aspect of succinct arguments is that of efficiency. So the verifier runs in time, which is polylogarithmic in t, where t here is the time to verify the NP statement. So you can think this is the running time of kind of the verification machine for this language. Or if, in other words, if the prover just sent the witness in the clear, this is the time it would take the verifier to check the witness with to check the statement with the full witness. So t here is kind of the running time of interest. And efficiency guarantees that the verifier runs in essentially time which is independent of this time-bound t. And furthermore, this is also true of communication. So the communication is also polylogarithmic in this time-bound t. And together, these are what make this argument succinct, and we think of these as very good properties and what makes kind of succinct arguments useful. On the flip side, however, the prover may run in some arbitrary polynomial time in t. And in general, this could be a huge bottleneck for using succinct arguments actually in practical applications. So as a running example, I want to consider the task of delegation. So this is where some client computer has some computational task, say compute this machine M on some input X, that it sends to a kind of more powerful server like AWS. So AWS is going to compute the output Y of this computation. However, naively, this requires that the clients actually trust the server at hand. To alleviate this trust and to instead trust in, say, some mathematical guarantees, the client and server may interact and provide some proof that this computation was actually done correctly. And this general strategy is one where the server first computes the output and then does some sort of proof to convince the verifier that it's the correct output. And in particular, you can use a succinct argument for the statement, which says this kind of encoding of this machine on some input X outputs some value Y. But the problem here is if we're using a succinct argument where the prover's overhead is some polynomial in the time-bound t, say t squared, then if this original computation maybe takes t time to compute, where t is like 2 to the 40 steps, this corresponds to about an hour-long computation, then the time to compute the proof would be over 400 million years. So this like overhead of computing the proof, even though it's kind of polynomial, which is nice in theory, for many practical applications where this computation is large, it's just completely impractical to then provide a proof on top of it.
Why do you get 400 million years?
So I plugged in 2 to the 40 nanoseconds or something and got 1 hour. And then when I plug in 2 to the 80 nanoseconds, I get 400 million years.
Yeah, I guess it depends how you measure. Huh?
Yeah, these are very made up numbers, but I think the main point is that when the original computation is large, as such in the case of delegation, this blow up is very impractical. So what's the state of the art for this task? And in particular, I'm considering the general task of succinct arguments where the prover has some witness for an NP, for a general NP language, and we allow interaction. So what we know as far as prover efficiency goes is it essentially seems solved from a theory point of view in the sense that we have these t times polylog t solutions. And recall, I'm thinking of polylog t as kind of being this small factor, which is essentially independent of t. And at a very high level, these constructions follow from efficient PCPs or probabilistically checkable proofs, which are kind of these long strings that the verifier can very efficiently check statements given this encoding, which can then be compiled down into a succinct argument using Kilian's protocol. And so one kind of bottleneck of improving this efficiency is the fact that we currently, we've studied PCPs for a long time and we don't have any kind of good general purpose PCPs with very small overhead. So say linear overhead to compute the PCP from just the witness itself. But even for this case of delegation I talked about before, even a factor of 2 overhead may be too much. For an hour-long computation, maybe I'm not willing to take another hour of my time to get a proof back. So one way around this is the use of parallelism. So for example, this work by Ben-Sasson, Chiesa, Genkin, and Trummer in 2013, they show how to construct this kind of efficient size t times polylog t PCP, which is the best we currently know, where after you've computed the computation, so say after you've computed the verification circuit, you can compute the PCP in very low depth. So in only polylog t depth. And what this does when you kind of translate this into an argument, this gives a succinct argument where the prover runs in t plus polylog t parallel time, but with but this will require, say, t processors. So again, when t is like 2 to the 40 for your hour-long computation, this just becomes completely impractical if you want to kind of push down this efficiency to be maybe as tight as possible. Was there a question? Okay. So just to recap the prover efficiency landscape, starting with these original works on PCPs, followed by, say, Kilian and Macaulay's work, which show how to translate them into succinct arguments, or in the case of Macaulay's protocol, succinct non-interactive arguments. These give succinct arguments where the prover runs in polynomial time and uses just, in this case, 1 processor. As kind of improvements in PCPs were made, this work by Ben-Sasson and Sudan in 2005 shows how we can construct these efficient quasi-linear size and PCPs, where the number of processors here again is very small. And then kind of leveraging parallelism, this work from 2013 shows how to actually parallelize these PCPs. But then when you think of this as an argument which has very little overhead, it requires, say, a linear number of processors and the time to verify the circuit. And so what we want in this work is kind of getting the best of both worlds. Can we get an argument that has very tight overhead while requiring still very few processors? So this is kind of how we're situating this task. And what I'm talking about here is this notion of SPARKS, or succinct parallelizable arguments of knowledge.
When you say few, what do you mean? How many?
So I'll get to it in a bit, but I mean polylog t. Ideally, it'd be 1, but maybe that's too much to ask for. So for SPARKS, the idea we want to kind of put forth is that we want to try to leverage as much as possible the idea of computing the proof in parallel to the computation. In particular, this protocol is only going to receive as input some machine M, an input X, and a time-bound T. And so it doesn't a priori know the output. And here, for kind of general NP languages, you can think M is just your verification circuit. And what we want from a Spark is a succinct argument of knowledge where a prover both computes the output of the computation as well as a proof with the following efficiency guarantees. So first, it runs in T plus some additive polylog T terms, where this is parallel time. So the number of processors we allow it to use is polylog T. So you should think of this as an hour-long computation takes around an hour to prove. However, we allow the prover to additionally use some number of processors, which shouldn't grow with T.
M is a circuit?
So in this work, we're thinking of it as being a RAM machine. But yeah, and I guess to get this kind of tight overhead, yeah, it's best to think in terms of RAM machine. For circuits, we would need to somehow compile it into a RAM machine, either parallel RAM or otherwise, which may incur some extra overhead. But yeah, I should have said this is like your verification machine thought of as a RAM machine. So what we achieve in this work, first we show that there exists a spark, which runs in 4 rounds, assuming only collision resistance. And second, if you assume kind of stronger underlying object, a succinct non-interactive argument of knowledge, where the prover runs in quasi-linear time. So this is where the prover runs in time t times polylog t for verification machines, which take time t. So assuming this stronger object, we show how to actually construct a non-interactive spark. And underlying our main results is a transformation which takes any general t times polylog t, so quasi-linear overhead succinct argument of knowledge, and translates it to a spark, assuming only collision resistance. And the way I want you to think of this transformation is we start with some argument, which maybe for an hour-long computation takes 1,000 hours to prove. And we're trying to think of trading off the time it takes to prove this with the number of processors. So then after this transformation, we can get a argument which takes an hour long to compute and both compute and prove the computation, but uses say 1,000 or a little more than 1,000 processors. And for concreteness, the first theorem applies by kind of plugging in Kilian's 4-round succinct argument into this transformation. And the second non-interactive spark result comes from inserting a non-interactive succinct argument of knowledge into this transformation.
Cody?
Yes.
I didn't follow. Beforehand you say that we don't know how to achieve spark with prover time, with linear prover time, right?
This is this.
It was PCP?
Yeah, so before I said we don't know PCPs by themselves that have this linear overhead. Is that what you're referring to?
Yeah. Okay. Right, yeah.
Okay. Okay, so yeah, the focus of this talk will kind of be on this transformation, and hopefully I'll give an idea of how it works and kind of the main techniques behind it. But before I get to that, I want to focus on a few applications of Sparks. So the first is to kind of this running example I had before of time-tight delegation. So what do I mean by this? I mean that if some client wants to compute some machine, some RAM machine M on input X, the server can use some non-interactive Spark, in this case just for deterministic computation, just appends that with the result of the output of the computation. And this gives an immediate delegation scheme where the prover only runs in this kind of close to optimal T plus polylog T running time, where here the time bound T is the time to compute the computation. And plugging this into our theorem from before, it shows that assuming collision resistance and a quasi-linear snark, we can achieve this kind of time-tight delegation scheme generically. And furthermore, I want to emphasize that this can... What was that?
With N? Snark with N?
I could not understand the question.
I didn't hear the question exactly.
Snark with N?
Oh, so a snark, by that I mean a succinct non-interactive argument of knowledge.
Thanks.
Okay. Yeah, so what this shows is that given a succinct non-interactive argument of knowledge, from our transformation before, we get a non-interactive spark, which then gives a time-tight delegation scheme. And I want to emphasize that this works for any arbitrary computation. In particular, if we start with a sequential function, so this is a function that can be computed in some time t, but not faster, even if you have a lot of parallelism or preprocessing or some other kind of advantage. And so you should think of like a sequential function as a kind of computation which can't be sped up. And so it provides this kind of time guarantee. And a verifiable delay function is just this kind of slow sequential function that additionally outputs a proof of correctness, which can be verified much quicker than time t. And so our observation is that if you have this non-interactive spark and you just use it for a sequential function, this immediately gives a VDF. So this is kind of a generic construction of a VDF from any sequential function. And again, what this shows is assuming any quasi-linear snark and collision resistance, we can do this transformation. So this gives kind of a generic construction of verifiable delay functions. And a point I want to emphasize is that previously we only knew such generic constructions when we started with very specific sequential functions that were iterated. And what I mean by this is something like an iterated hash function or repeated squaring and a group of unknown order. Okay, so previously such a transformation was only known for specific sequential functions. And why it's kind of interesting to capture these arbitrary sequential functions is if it satisfies some other hardness property. For example, if the sequential function is also memory hard, this will also be preserved by the transformation. So again, just plugging this in, start with some memory hard sequential function, apply some non-interactive spark, and this will give a memory hard VDF. And what I mean by memory hard here is that the kind of bottleneck to computing this function at a high level is memory accesses. And why this is important is that a lot of these kind of sequential functions that have been used to construct VDFs, by the nature of the computation, it encourages people to kind of buy special purpose hardware to compute these functions. And by using a memory hard function, the idea is that kind of common computer architectures are the best tools we know to compute these functions. So they provide this kind of level of ASIC resistance for these primitives. And furthermore, we know of at least candidate memory hard sequential functions, which are proven secure in the random oracle model. So then by instantiating this random oracle with some concrete hash function, we get a candidate memory hard sequential function. And then applying our transformation, this gives a candidate memory hard VDF. So there are a lot of kind of steps to this process, but kind of I want to emphasize that this is kind of the first candidate along these lines that we know of. And as I said before, this is useful for kind of getting rid of the reliance on special purpose hardware like ASICs for various blockchain applications where VDFs are used.
Could you please repeat what's the notion of memory hard? Memory hard?
Yeah, so I'm not formally defining it here. And in fact, there are kind of many definitions you could possibly consider. But the high level idea is that the main bottleneck to computing the function is the memory accesses that you make. So for example, improving kind of your local hardware computation is not going to improve the amount of time it takes to compute the function by too much. Does that make sense?
Yeah, I think so.
So I'm going to have to kind of make a bunch of sequential accesses to memory. And to speed up the computation of the function, I would need to kind of improve how fast I could access this kind of random looking memory calls. And there are different notions like cumulative memory complexity that define kind of the average number of memory accesses required to compute a function, or sustained memory complexity, which says in order to compute the function, I must kind of over the whole course of the computation make many accesses, or kind of your standard space complexity maybe is of interest, or there are a variety of notions.
It sounds related to the notion of proof of proof of space.
Yeah, so you can think a memory hard VDF would be a proof of space. I don't know 100% how true this is. There are also many different proof of space notions, but a proof of space which also provides a unique function output. So for a lot of these applications of VDFs, it's important that there's actually a unique output which may be used to generate, say, a random value that everyone can agree upon. And you don't want it to be the case that there are kind of many ways to derive different verifiable outputs. Does that make sense?
Yeah.
Okay. But yeah, if there are any other questions about the applications, before I get into a construction, this would be a good place to ask. Okay, so as I said before, kind of underlying our main results is this transformation from a succinct argument of knowledge that starts with a quasi-linear prover and translates it into a spark, which now has this essentially optimal time, but using a polylogarithmic number of processors. And so for a construction, I'm going to make a few simplifying assumptions. One, I'm going to think only in a non-interactive regime, so starting with SNARKs. And two, I'm only going to consider sequential RAM computation, and I'll briefly touch on how to deal with these later. So to start off, I want to consider SPARKs for computations which have very small space. And this was considered previously in contexts of verifiable delay functions. So here, kind of the picture to have in your mind is we have some computation which takes t time. So I'm using the horizontal axis here to represent time. And it takes t time to come up with the output y. And somehow we need to come up with a proof that's happening in parallel to this computation. And so what these previous works observe is that they ask the question, like, what if we had a SNARK for some specific or general purpose computation that has some small overhead? Say it has only, it takes t extra time for t time computations. So in particular, the overhead is 2 times t in total. And what they say is, given such an object, well, we can first start by just proving the first half. So if you take the first t/2 steps of the computation, you can compute it and then prove it and finish by time t, because we assumed that the proof just takes t, kind of takes an extra factor to compute, or to compute the proof. So what we've done is we've taken as much of the computation as possible, and then we've proved it. And then we can just kind of recursively apply this idea. So at time t/2, we then say, okay, we can compute t/4 more steps, as well as a proof, and finish by time t.
So that's
then,
with a different processor that we are describing now?
Yeah,
Like,
so here I'm thinking an additional processor can then create kind of this new thread, which computes steps t/2 to 3t/4, and then proves that and finishes by time t.
Okay.
And then after time 3t/4, we create a new processor, which runs for time t/8 to compute the computation and then proves it, and so on, until we get to some base case where, say, we just have one step of the computation. And here, the number of proofs we're going to need, kind of the number of sub-protocols we'll need to use, is only logarithmic in t. So this number m, I'm thinking of as the number of protocols. This is where we can kind of stop this recursion. And what this says is if we had any kind of sub-protocol for these underlying proofs, we'll now get only a logarithmic in T factor increase for the prover, verifier, and communication complexity, because the verifier will now need to independently check all of these proofs as well as make sure they all kind of fit together properly. And in general, so here we started with a snark which had overhead, which is 2 times T to split into this T over 2 size. But in general, if we have snarks that have this A times T overhead for any value of A, then the number of protocols we'll need will be some A times log T. So you can think if your overhead is A, we incur, say, a logarithmic overhead in the various complexity, factors of complexity. And yes?
M is the number of processors. M is the number of processors.
So M here, I'm thinking of as the number of subprotocols. So if you're only using 1 processor per subprotocol, it would also be the number of processors.
But you have to verify also that all proofs are consistent with each other, right?
Yes. Yeah, like, yeah, I'll talk about that briefly in the next slide, I think. But the point here is that if this overhead was only quasi-linear, that means this A value is just polylog T. So that's why our resulting protocol only needs a polylogarithmic number of processors and still satisfies the standard succinctness notions. So kind of coming back to the points made before, why doesn't this work? Well, the problem is that the intermediate statements for the computation, and these are kind of what the verifier needs to check for each subprotocol and also check that they're consistent with each other. They look as follows. They say that starting at some initial space of the computation, where I'm thinking of space kind of as your like tape for your Turing or RAM machine, representing all of your space needed for the computation. So we start with this space, we're running M for K steps, and then we result in some final configuration or space. And in particular, these statements will grow with the space of the computation. So in order to cut up the computation in these parts, I'm going to have to tell you kind of what's the configuration in each intermediate point. And so if this space has size, say, as large as the time to compute the computation T, then it doesn't seem like there's any hope that we can get the verifier to be polylogarithmic in this time-bound T. Because even to read the statement, it would need to kind of do T work. So our first attempt of how to fix this problem that our intermediate statements are too large is to just hash down this space. So in particular, instead of our intermediate statements depending on the space, our intermediate statements will depend on digests of the space. And what the prover kind of naively would prove is that there exists some initial space or configuration at the start and end of each subcomputation that are consistent with these digests. And starting from this initial configuration, running M for K steps results in some final configuration. And here I want to emphasize that this space, this initial and final space, is the witness for this subprotocol that needs to be run. And what this shows is that essentially we've just taken our complexity that was in the statements, that they were too large, and we've just pushed it to the witness of the prover. And this does in fact fix the communication and verifier complexity, but the prover here will now be inefficient because it has to do something in each of these subprotocols, which depends on the space of the computation, which may be very large. And so our next idea to get around this is actually change the way we're using these hash functions. So instead, we're going to use updatable hash functions where we have the exact same intermediate statements. We're just going to prove them in a different way. In particular, we're going to prove that there exists updates to these digests such that running this machine specifies these updates. You can think this update says like change one location to have this new value. So these kind of local updates. And additionally, now we're checking that the updates are consistent with the digest themselves. So starting at some initial digest, applying these K updates results in this final digest. And here the key point is that this witness now scales with the number of steps computed in each intermediate statement and not the space of the computation. So our kind of main question that we need to address is how to actually compute this witness for the subcomputation, the k updates, in parallel to the computation. And for this, we use an idea of pipelining Merkle trees to provide this kind of updatable hash function primitive. So what we do is we use Merkle trees with pipelining, and we have the same intermediate statements and proofs as before, but then I'll have this additional efficiency guarantee, which I'll go into next. So recall that Merkle trees, they kind of take some database or space of your computation. They first break them up into small chunks, and then iteratively, we're going to use hash functions to kind of take each pair and hash them down to a single block, such that if we recursively apply this idea, we keep cutting the space of our computation into these kind of summaries, which are half the size, until we get a single digest representing this whole database. And the reason that Merkle trees get used often is because they provide this kind of local update or read properties. So for example, say you want to update some location in your original database. So here I'm using kind of the purple blocks to denote the updated values. So I update some value in the leaf of this tree, and that's only going to affect the kind of descendants down to the root of this tree. And furthermore, I can prove that this is the only location I've updated by reading the siblings along this path. So this is the property we're using of Merkle trees, that these updates themselves are small, but we additionally need to compute them efficiently. And the way we do this is using this kind of idea of pipelining. So say we're updating multiple locations over many sequential steps. So first, maybe we're going to update location I1. So we can use one processor to read and write the corresponding location in the database. Then another processor comes along to do another update. And here the second processor can update and read the locations it needs to at the first level of the Merkle tree, while the original processor who's updating location I1 can do everything it needs to do at level 2 in this tree. And then again, for the third, if there's the third update that's called, we can use a third processor to access all of the elements it needs at level 1 in the tree. A different processor is working on the second update at level 2 in the tree. And then the original processor is still working on the first update and is currently on level 3 of the tree. And so this is what I mean by if we just kind of push all of these updates in this kind of pipelined manner, we can actually compute these updates in parallel to our original computation. So just to kind of go back to our picture from before, we're computing this kind of witness for these subprotocols, which consists of these updates to this hash function, which we're using this Merkle tree for. And the key point is that we can actually compute these updates in parallel to the computation with essentially no overhead. And so next, I want to kind of give a big picture of what this looks like as our full protocol. So we're now going to kind of put everything together. So again, on the horizontal axis, I have the time it takes to compute the computation. And to start off, we're just going to initially commit to an empty database. So this can be done in time independent even of the size of the database using Merkle trees. Then we're first going to run some number of steps, which I'll discuss in a bit. And in parallel to this, we can compute these updates to this digest that we initially have. So what this looks like is for each step of the computation, maybe it says updates some element of the space of the computation, does perform some write, then we can kind of perform this write to the Merkle tree and keep pipelining the updates as they come and do it in parallel to the computation.
So you need for that log n processors? You need processor level in the Merkle tree?
Yeah, so we'll need something like log n processors because each level is going to be accessed essentially at the same time. And it'll actually be a little more because there could be some delay between the time it takes to update each of the levels. So it could be that essentially the amount of time it takes to perform a Merkle tree update will be the number of processors we need working at the same time. Does that make sense?
So you have a processor per level, and you also have a delay.
So if it takes 100 steps to update the Merkle tree, to do the full update down the tree, then we'll need 100 processors to kind of do this work such that we're using as much of we're like getting all the benefit from this pipelining and able to do it completely in parallel to the computation.
One time, one time. So why is your box a little bit bigger than the K1 steps?
Yeah, okay, so the reason it's a little bit bigger than K1 steps is because we essentially have to wait for the last update to kind of flush through the tree. So this is like some overhang of, in order to compute the last update, it's gonna have some extra time to like finish the last update.
It's 1 unit, it's not like, we're saying it's 1 unit because you do everything in one parallel time.
So each update will need to at least touch each of the log n levels in the tree. So the last update to finish will then need to again access each level in the tree. So it'll add some overhead to compute all of the updates. So we're not thinking of each update as being one step, but they could be 100 steps. But the point is that they all can be kind of computed at the same time as if they were done sequentially.
So it should be, the box should look something like that. It's like the second processor starts to work only after the first one finished.
Yeah, so here, these three processors are all working at the same time, but the first processor still needs to kind of work through each level of the tree to compute the full update.
Okay.
Okay, so what we've said so far is we have this initial hash, we do some steps of the computation. In parallel, we're computing these updates, and these updates are used for this subprotocol, which proves correctness of this kind of first K1 steps of computation, using this statement, which says this machine M on input X running for K1 steps goes from this initial digest 0 to this final digest 1. And the way we choose this number of steps is simply how many steps can we compute, update, and then prove, and finish in time t. So all we do is, at this point, is we just recursively apply this idea. So we do some K2 number of steps, which is, say, the most number of steps we can compute, update, and prove, and finish by time t. And then, again, we do this at time K1 plus K2, etc., until we get down to some base case where, say, we don't even have to prove it, we can just directly have the verifier check this statement. And the point I want to kind of bring back is that if this snark had only quasi-linear overhead, then the number of protocols here we'll need will be this M value, which is only polylogarithmic in T. And we're doing so in a way that everything finishes in parallel time, which is essentially T. And we'll have some polylog T overhead to kind of finish computing these updates, which is where that comes from. And furthermore, I want to kind of remind you that the complexity for our Spark, meaning the verifier's complexity, the communication, and kind of the parallelism, is all M times that of the underlying snark, where M here is just some polylogarithmic term which depends on the overhead of the underlying computation, the underlying snark. And furthermore, just briefly, I want to mention that we're doing all of these underlying protocols in parallel And so to show argument of knowledge, it actually requires composing all of these kind of underlying extractors for this argument of knowledge proof.
Wait, why is it m times? Isn't that just linear?
Like essentially there are m separate protocols being run to prove this overall computation. And so if the underlying protocol has some complexity, the verifier needs to check m kind of independent protocols.
But it's not that the instance getting smaller? You're saying it's not getting smaller. The picture is, I see. It's actually linear database all the time. So it's m times. You know? I thought that it's going smaller and smaller, and because it's getting smaller, it becomes like metric, but it's not because it's the data is linear all the time. The RAM, the memory.
Yeah, so the memory will stay, or the memory will again be only this like m times the amount of memory each of these subprotocols need. And in particular, if the subprotocols don't require more memory, then this will also not be too much more. I don't know if that answered your question. I'm not 100% clear what you're asking.
I have another question.
Okay.
Is any of this process need a different memory? They don't access the same memory?
So you can think that there's like a main computation thread, which is performing the steps and the updates and is kind of constantly running throughout and is kind of sharing memory. But each of these underlying protocols we can think of as having kind of completely disjoint memory once the witnesses for those protocols have been computed.
But they should keep check the main memory. No? Okay.
So I guess what I'm saying is they don't need to, I guess like you have the memory of the machine that's being run, and then you have kind of the extra memory by the prover. And for each of the subprotocols, it's once we've kind of computed the witness for the subprotocol, it can be completely independently run from kind of the main memory of the computation.
Okay. Okay, thanks.
Okay. Hopefully that, yeah, there are like a lot of pieces coming together here, and really you should think that all of these subprotocols, once the witnesses have been computed, are essentially independent of each other, and we're just using an off-the-shelf prover and verifier for the underlying snark to check all of these independent statements.
Okay.
Small question about the initialization. You said that you start with an empty database, but you could also start with like a database that is filled with some initial data, right?
Yeah, so if, say like you've already done one computation or something and proven that, and you have some hash of a database that already has all the information stored and that's agreed upon before the protocol, you could start with that. However, in case the, say, witness is very large, we don't want the prover to have to compute a hash of the database initially or have the verifier agree that that's the correct value ahead of time, which is why we start with a hash of an empty database. And then you can think, if you do like a first read, the prover will prove that like I'm writing a value that I would have written, or I'm writing a value that I would have read for the first time. So yeah, that's a subtle point of, in order to make this efficient for both the prover and the verifier, we just hash an empty database and we update it. Say the first read, we actually write to that location.
Okay.
But for a Merkle tree, for example, you can hash an empty database since all of the leaves have the same value. So you can just do like log n hashes. So that's another place where we have this kind of polylog overhead. Okay, so I'll briefly pause again in case there are any other questions about the kind of main protocol. Okay, so next I want to kind of briefly touch on the interactive protocol, and also then I'll talk about how to deal with kind of parallel RAM computation as well. So for interactive protocols, first I just want to point out that if the underlying argument is interactive, the same idea from before kind of just straightforward works, and the Spark will also be interactive. So each of these subprotocols will now introduce kind of their own rounds of communication. And so naively, just as with kind of these other complexities, the rounds will also increase by a factor of this number of protocols M, which is polylog n T. However, sometimes we can kind of be more clever and sync up the messages from the underlying subprotocols. And in particular, this is how we get our result for a 4-round Spark from Kilian's protocol, because the first prover's message is actually kind of the most expensive part of the protocol and dominates the prover's running time. So we can essentially run the protocol as if it's non-interactive for the first prover message, and then all the remaining rounds take very little time. So I'll give a picture to hopefully summarize this idea. So whenever we're applying this to Kilian's protocol, where the first message is kind of computing a PCP for some intermediate statements, we have the same exact picture from before, but now we kind of stop after the first message of the prover. And then in the remaining polylog T time, we can kind of finish off Kilian's protocol in parallel. So we can send all the PCP digests, and then the verifier will like send challenge queries, and then the prover can respond to all of those at the same time. So this is a very high level idea of why we don't always incur this factor of M polylog T overhead in the number of rounds, and we can get this 4-round Spark using the blueprint from Kilian's protocol. So now I want to next touch briefly on handling parallel computations. So the main bottleneck from before is that using hash functions, so Merkle trees by themselves, usually you're only using them to update a single location. But if we allow the hash functions to update many locations at the same time, then our construction can extend to the parallel RAM setting, where you're sending queries to like update multiple locations in memory at once. So in particular, we have kind of a database and a corresponding digest. If we allow it to update kind of sets of locations all at the same time that give some new digest with a proof, this allows us to handle parallel RAM computations.
Not sequentially, like what are you trying to, what's your target, what's your goal?
So like normally with Merkle trees, you say update one location and you get a path, a like authentication path for that location, which convinces you that this location has been updated and is valid. So I want to now say you can, if the underlying computation updates 5 indices at the same time, you can update all of those and compute a proof in a way that all of this can be done in parallel and pipelines before, as I said before, but where you're now touching like 5 locations in memory for each step of the computation. Does that make sense?
Mm-hmm.
Okay, so essentially what I'm saying is if our hash function, or you can think if we can extend Merkle trees to do this more general like parallel updates all at once, then we can handle these parallel computations. And there's a bit of a sub-technicality. In particular, the number of subprotocols we'll need here will depend on this kind of parallelism bound P, which is the number of kind of the size of the set that you'll need to update at once. And so this is one reason why naively using this approach will only be able to handle SPARKS for computation, which have kind of a bounded number of processors that it's using. So parallel RAM with only polylog T processors. And we're currently working on improving this to extend to kind of all parallel RAM machines, which could have some arbitrary even T processors working at the same time. So next, I just want to briefly conclude. So what we showed in this work is this notion of SPARKS, which are succinct parallelizable arguments of knowledge, which we show how to compute and prove non-deterministic, even parallel RAM computations, where here, for the time being, we only consider bounded number of processors for the parallel RAM computations. And we do this using, where the prover uses T plus polylog T parallel time and only polylog T processors. So this is essentially T time with very few processors. And this follows from a generic transformation, which takes any quasi-linear succinct argument of knowledge and constructs SPARKS, assuming only collision resistance. And the idea I want you to kind of take away is that at a high level, this gives a way to take any function and make it verifiable. In particular, we give candidate memory hard VDFs as a result. And my final thing I want to leave you with is that this work we see is very much a theoretical feasibility result for now. In particular, there are a lot of gaps between this kind of theoretical RAM model or parallel RAM model and how computers actually work. And so I think it gives a promising idea that we can compute these proofs with very little overhead, but there's still lots of work left to make it practical. So I think it leaves a lot of questions open, both from a theory and a practice perspective, and hopefully add something new to this conversation of how do we create these efficient delegation protocols or general succinct argument protocols. So yeah, thank you.
Thank you so much. Any questions?
Yeah, I have a question. Thanks, Cody. Great talk. About the construction with the collision resistant hash function, you can probably abstract it to any commitment scheme that is succinct and allows locally decommitment. Can you do that?
So we formalize in our paper, we call it like a concurrently updatable commitment, which says like what kind of updatable hash function, or this is the slide I want. What kind of updatable hash function can be used in this setting? And I think the biggest problem of kind of using other ideas is actually computing all of these updates in parallel to the computation so that the picture kind of looks like this, where it can be computed at the same time and only has some very small overhang of the underlying computation. So yeah, the hardest thing to achieve with other approaches is most likely this like efficiency guarantee of kind of doing all of these updates that only have an additive overhead when you're then applying it to some computation here. Does that make sense?
Yeah, but more advanced accumulator style commitments, wouldn't they support this property already?
Sorry, what style commitments?
Accumulators.
Oh, accumulators. So we looked briefly at accumulators, but we didn't spend too much time. But it wasn't clear exactly because, yeah, I guess we had looked at it and we think it's interesting of if a more algebraic style a construction of these kind of vector commitments would work. But we weren't able, at least from our initial thoughts, able to show this efficiency property. But we definitely think that's one of the lines of interest of making these more practical, because I know there's a lot of problems with these Merkle trees in general rely on hash functions. And as I said before, kind of the number of parallel processors we need depends on the time to compute, say, like log n hashes, which could be kind of unreasonably large, even though it's like theoretically nice.
Yeah, great, thank you.
Okay, any other questions? So thank you, Cody. Thank you so much.
Yeah, and thanks for inviting me.
Thank you. Thank you so much.
Thank you.